solar energy has come an extremely long way from where it was just like 20 years ago. I mean, we are seeing more and more homes equipped with solar, and solar is one of the cheapest forms of energy out there on the market. And so it's become not just something that makes environmental sense, but something that makes just business sense as well. But there is something holding us back from really making that complete energy transition. And that's trying to get to extremely high temperatures. And I mean like really hot, like 1500 degrees Celsius hot. And when things need to get that hot, solar power just falls short because it's losing almost 90% of the energy in transmission that it started with. However, in this interview with Leo and Giant Leap Technologies, you will hear all about how he's creating a nanotechnology that bends light and makes it software programmable, meaning that we can control where the light goes and concentrate it, along with a variety of other applications. And so make sure you stick around for the entire interview to hear exactly how this nanotechnology is going to be revolutionizing our energy transition. Leo, do you mind telling us a bit about Giant Leap Technologies and what you guys do?
Hi, Billy. Sure. Thanks for the opportunity. I'm a research physicist and engineer by training, and I've worked a lot in the national laboratories. And I've developed, after leaving the laboratories, a company called Giant Leap Technologies. And we're developing a nanotechnology to bend light and to make light and optics software programmable. And this is a new approach to doing optics with a lot of potential applications.
Very cool. And what are some of those applications that you see for this technology?
Oh my, there's a lot that can be done with a programmable piece of glass. You can imagine a piece of glass that you can make anything you want just by software programming it. It's an amazing possibility that you can take a piece of glass and software program it to become anything that you would like. And applications of this run from augmented reality to LIDAR for autonomous vehicles, to medical applications, and certainly solar energy, which is one of the leading applications for the technology.
That's awesome. So you're talking about programming glass. So how do you go about programming glass? What is the glass made of? Let's dive into more detail there.
So the technology was originally called the particle swarm optics, which sort of gives a hint as to what it might be. And the name has actually evolved a little bit. It's now optometaphoresis, which is more scientific and useful for talking to the greater scientific community. And what it is an ability to manipulate light by migrating nanoparticles within a liquid within the glass. So we have translation of particles, and we have rotation of particles, and even deformation, the shape of the particles, to scatter light in an unusual way and send light from one direction into literally any other direction that is desired by low-level electrical signals that are applied in close proximity to the liquid. It is interesting because it has a capacity for really high power and for really large areas and over large temperature ranges, which you can't get with anything that's out there today. So it has a really unique niche that it might be able to serve.
Yeah, definitely. So this could be used for solar panels then get in places that are really hot, like Arizona or out in the Middle East. They're getting a lot of sunlight, but their lifespan is like cut in half because of the fact that they're just getting so much heat on these solar panels. It's just not good for them. So this is solving some of those issues, right?
Yes, I mean, I think the actual application in solar is a little bit different than photovoltaics. So the real underappreciated, I think it's the right way to say it, underappreciated application in solar is intense heat. So we're talking about temperatures as high as 1,500 degrees Celsius. And there's nothing out there that can really do that right now, except for some of these concentrating solar arrays. And the thing that most people don't appreciate is that they throw away about 90% of the sunlight. They just let it fall to the ground. So the ability to cover the entire area with a solid, effectively a solid state solution, allows you to get as much as 10 times more per unit area. And that is a pretty big deal. And I think the applications, just to get you centered on it, there's 4 critical technologies or materials, I should say, for our civilization: ammonia for fertilizer, steel, cement, and plastics, all of which, and their derivatives, all of which require a tremendous amount of heat. And if one of those just disappears, if you don't get ammonia, you don't have the ability to have fertilizers, and the civilization doesn't go rolling along as well as you'd like it, to say the least. So there's a desperate need for solving intense heat for these materials, and it accrues to about 25% of the total carbon emissions every year. So it's a big deal if you can get one technology to knock out as much as 25% of global emissions.
Yeah, definitely. That's huge, because in these industrial applications, you have to get those very high temperatures. And with current solar panels and other things like that, it's really difficult to do that without using fossil fuels.
That's exactly right. The fossil fuels cannot be removed from this particular application, these four materials and their production. And if you try to do it with photovoltaic, a panel might be, being generous, 20% efficient. And then they rotate the panels and they point them south, and there's light that falls between the panels. So you're throwing away more energy. And then you've got to put it on a transmission line, and you're throwing away more energy. By the time you get to your end user who needs to make intense heat, you've thrown away 90+%, if not more. And that won't work. For one-offs it'll work, but if you want to change the planet and you don't want to have fields as far as the eye can see of photovoltaics, then you need a different solution.
Definitely. And so with the particle swarm optics, is it a similar application to where you'd be with the solid state over the ground? Or like, where would it be? How can we visualize this?
Oh, here's where the fun starts, because most of the systems that are out there today for concentrating solar have a big central tower, hundreds and hundreds of feet high, meters high. And you might have a mile wide, 2-kilometer wide or diameter field of mirrors, thousands upon thousands of mirrors. And they have big mechanical steering and all that. Imagine if you could just eliminate all the concrete, all the steel, all the motors, and you just were to lay out a piece of glass or roll out a piece of plastic that has the technology in it, a transparent piece of material. And the light, you put a signal on it, a few kilohertz here or there, very low level signals, and the light basically just directs itself to the focus. That's a big deal. And it can be done in such a way that you don't need to have the central tower. You could do that, of course. You could reflect the light, or you could transmit the light, and you could focus it internal, so a containment building, so that no heat gets out into the environment, and it protects the wildlife. Unlike today's systems, which can have the possibility of killing birds by incinerating them, and even if that problem is being corrected by various techniques, it is still there. And also the large area overruns the fields and has an ecological impact. So if you were to reduce the size of your plant by a factor of 10 and increase your energy on your facility, on your target, which might be making ammonia, for example, and it's inside a containment building, wow. And you can use it for multiple things. You can use it for that, for making the ammonia, or for steel, or you can use it for any one of a number of things, including electricity generation, of course, with the day-night heat storage.
Yeah, definitely. So are you thinking these will be placed like on buildings or out in fields?
Both. Buildings can be used for, it's called daylighting. So basically controlling the energy within a building with glass windows that have some smarts to them. So that's one application. But in terms of intense heat, it would be closer to the city centers, which means it's closer to workers, which means that you can do real industry and have from people that can access the facilities to do the jobs, or robotics as well, and all sorts of things that are easily serviceable by people that are not well out in the deserts. And also, I think it creates an economic opportunity beyond the solar. It becomes a central hub, because such an amazing capacity for heat and electricity generation. You do all sorts of things simultaneously. You can desalinate water. You can create hydrogen. The hydrogen can be used to create steel, okay? And also for creating ammonia. So all these things become central in one location, perhaps close to the oceans, bodies of water. It becomes this amazing catalyst for a community to create jobs and do amazing things for our environment as well.
Definitely. And so being able to concentrate it all to the center, does it have to be transmitted immediately, like the heat and the energy? Does that have to be immediately transferred out, or can you put it into like a battery something and transfer it somewhere else? How does that work?
Great question, Billy. And I think the way I envision it at this time is you would have heat storage local to the facility, which would allow some, perhaps not all, but some products to be done day and night, independent of the weather, for example, or the darkness of night. And The capacity to do transformations like carrying a battery, if you will, is possible. It hasn't been what I've been focused on. The focus here is mostly on the light control as opposed to the storage. And there are other folks that are making amazing strides in that area.
Okay, I got you. Cool. So let me take a step back. What is your mission with Giant Leap Technologies?
Sure. I guess the sort of the tagline version of it is to power, protect, and propel humanity into the future with directed light. So directed light energy has historically been associated only with the Star Wars initiative, throwing high-powered laser beams around to do various things. But I'm expanding the definition wherein it could be low-level signals, it could be very tiny amounts of light, but you're directing that light with software control over large areas. It could be a large area, it could be a lens augmented reality display that you're wearing, or it could be meters, many meters squared per panel, or even the size of a football field, so to speak. So that capacity to channel energy from many different scales and to do it over high powers, potentially sunlight or high powered lasers as well, and over large temperature ranges is unique. Let me just give you, for instance, typically today, one of the techniques people use for electronics light steering is liquid crystals. And the liquid crystals can be manipulated to change the refractive index locally and to try to bend light a little bit. One of the problems with liquid crystals is they have a very narrow temperature range. But what we are working on is something that has a temperature range from minus 50 Celsius to over 100 Celsius. Wow. You could use it in many places, and it's not far off from space applications too, even if you had some heaters and low-level heaters and stuff, perhaps even in orbit. So it is an amazing capability to shift from liquid crystals to colloids that have nanoparticles in them. And this is where the research is right now. It's early stage, so I don't want to give the wrong impression. We're still in the early stage of development. All the math is there, and it's looking very good. And interestingly, all the different components that have been developed in hardware by other developers and other researchers. So we just need to integrate everything together. And the tall pole, if you will, right now is the chemistry for the colloids. We have to get that just right. There's a lot of technical issues, which I won't go into here, but there's a lot of nuance that has to be done right in order to be able to put an electrical signal on it and have it steer light just the way you want.
Gotcha. So you guys are working on that technology now to get it to steer the light in the way that you're hoping for.
And as a precursor to the final systems design, we're doing the chemistry right now. So we're at the stage where the chemistry has to be done. It has been demonstrated before, so we're confident, very confident it can be done again. The question is, how can you drive the costs down? How can you do it over large production volumes and things of that nature? And that's a challenge, right? So we're currently looking for partners and things like that to help us with the chemistry. And I guess the model that we're having is more like a biotech startup, because there's a lot of capital equipment and a lot of deep tech you have to do up front in order to be able to pick those fruits, to harvest those intellectual fruits later on. And we are at that sort of stage where we're talking to folks in the government and investors and such, and trying to move things along. Hopefully within the next year or two, we'll make some decent progress.
Awesome. And so what led you to start using this and creating this as your next endeavor?
Oh, wow. Well, it's a long story with many twists and turns, and I won't go into all of it, but in broad brushstrokes, I was working at the NASA Caltech facility called Jet Propulsion Laboratory. They're the folks that send like the Mars rover to Mars, and they have just it's a wonderful place to work and many amazing opportunities to investigate things. And one of the things that I bumped into while I was working there was the remote sensing capabilities that they have to measure the atmosphere, to measure other planets. And when they do that, they practice on Earth first. It makes sense. And I was able to see a lot of the data that was coming in about global. And it was clear that it was an accelerating existential problem. And long story short, I decided to try an entrepreneurial hand at it to do something about it. But that occurred in combination with having this wonderful opportunity to work with a fellow by the name of Jonathan Dowling. He's a quantum physicist at the Jet Propulsion Laboratory, recently passed away. And he introduced me to metamaterials. These are engineered materials at the molecular or atomic level, typically nanoscale in my case right now, where you do something to make these materials. Typically it's been static. You build them somehow and then they're there and you've got it. But I've been curious on how to make them dynamic, so you can put signals on them and have them change from one type of metamaterial to the next. And so I guess those two things, the information about how the planet was changing and these introduction to metamaterials at Jet Propulsion Lab helped push me to try my own company. And I guess one of the other things that really is interesting is that for my personality, I didn't like being just a small cog in a big project. I mean, if you're putting something in space, it takes thousands of people. And I like to do it all, at least initially, just to have the fun on doing the initial work. So I was compelled by my personality to try to do something from beginning to end, and then to pass it off as we get the company going to a team of people.
Definitely, that's awesome. And so you've done a lot of projects in the past where you've worked on ultra high efficiency solar tracker and a whole lot more. So which has been your favorite project that you worked on before? And which one do you see as having the biggest application?
Most of the work that I've done has been at a national laboratories and has been developing early stage prototypes for the government to evaluate and to see where they were going to go. And some of the fun work that occurred was in two areas. One was in superconducting antennas. Honestly, that seems off base for the optics that I'm working on now, but not really. Antennas typically are like phased array antennas and such, which are typically big at microwave frequencies. But the hope has always been to be able to shrink the antennas smaller and smaller to make optical. And then when I got to work on these metamaterials, one project was out of DARPA to make a high-powered solar pumped laser project. I worked with DARPA, and that made me think a lot about phased arrays being smaller, because the metamaterials are these periodic structures, if you will, just like a phased array is. And then we started thinking about colloids, which are random particles floating around in a liquid that you can control. You can grab hold of it with electric signals. And it became this intellectual challenge of how do you make random arrays do something practical and pragmatic? And that has led to this optometaphoresis, often called swarm optics, where you can control the scattering of light, basically the refractive index you're controlling right down to the nanoscale with the coarse electrical signals. And that has been really exciting. And maybe, if all goes well, it will lead to a new capability in optics and a lowering of costs and a new capability for solar, for example, to replace these fossil fuels completely with the sunlight.
Yeah, that's really awesome. And you mentioned optical antennas. Can you describe that a little bit more? I've never heard of them before.
This is not something new. Lots of people have been working on optical antennas and optical antenna arrays, and you can find it at certainly all the major research universities from MIT to Stanford and all the others in between have their hand on something like this. And basically, an antenna, a classical antenna, will take an electrical signal, such as something you might have in a cable, an RF cable, and will be a transducer to the world outside. It will allow that electrical signal that's in a wire to be sent into space, and the electric signal becomes a wave in space. However, as you make the devices smaller and smaller, you can make the frequencies get higher and higher as you move towards light. But there are limits. There are practical limits. There have always been these practical limits. And yet, there's been this capacity for lithography that we've used to make computer chips, for example. And so we know we can make things pretty small, right down to the nanoscale for transistors, for example, for computers. There's always this opportunity where if you knew how to control the light and move it around on a chip, then you could send it to an antenna on a chip. And that antenna, again, would be a transducer that moves from a signal that's guided to a signal that's out in free space. And that has been the way that folks have been approaching it. Here, however, we're taking a slightly different approach, and we're saying you have a floating antenna in the colloid, in the liquid that we're doing, and we change the scattering properties of the liquid so that each particle, and there are trillions of them, potentially certainly on an augmented reality lens, it'd be trillions of these nanoparticles, something like 100,000 nanoparticles per cubic micron. So that's a lot of nanoparticles, each being controlled, but randomly positioned. And we're trying to use each of those as antennas, essentially, where we can change the phase and we can do other cool things to simulate a change in refractive index. And the refractive index is all about optics. And by the way, if you can do it, you can change not only the ability to bend light, you can also make sources of light that are unique. You can make red, green, blue laser sources that might be used for incredibly crisp monitors that you use on the computer screen or for other applications. There's all sorts of unique and interesting down the road applications. Refractive index can also be gain for a laser or loss for other types of attenuators to control or modulate light. Really interesting and fascinating stuff.
Yeah, I mean, that's all very fascinating. So let's move on a little bit here. What are your goals for Giant Leap Technologies in 2022?
I would say for 2022 and 2023 is to definitely get that funding going. We're really in the early stages of doing the demonstrations. and actually doing the demonstrations. So it's been a tough road, and I wish it was easier. And the national laboratories are very hard on getting funding, for example, the grants that are allowed. You have to have everything just right. And that's great. That's give value to the taxpayer. And we're closing in. I think we're pretty close to having that worked out. And hopefully we'll get some good funding where we don't have to dilute the ownership of the company early on. And once we have the demos in hand, we will probably open up to more conventional funding methods like venture capital and other investors.
Very cool. And what are you learning right now?
I guess the different categories of learning. On the business side of things, I would say everything is probably 2 pi more difficult than you thought it was going to be. It's a running joke, and it's true. It is just a lot harder, especially in hardware. Oh my gosh, hardware is, as the joke goes, is hard. And it requires a deep understanding of your subject, as well as convincing people who've never seen something before. It's hard to do that teaching. Software, I think, is probably a bit easier to do. It's not what we're doing right now, although eventually software will intersect what we're working on once we have the devices. On the technical side, there's lots of little nuance to it, but a lot of the chemistry is not average chemistry. And so even bringing in experts is a challenge. It takes a very special type of expert to work on a very special type of system to get exactly what we want done. And we know those people, but boy, it's hard to find them. So,
yeah, hard to suck their time away.
It's every little thing, no matter how trivial, is a big deal, especially when you're a little company. But we think it's worth it. I think it's worth it. And the world needs dreamers and the world needs doers. And so when I was at the national laboratories, we saw what the problems were with remote sensing. We could see the world was in crisis. And the question is, what do you do about it? And there are very few people that can come up with new ideas. And I will tell you, just for your viewers' sake, that this effort probably started in about 2005 and went through a lot of dead ends. And it wasn't until probably 2013, working full time on this, I might add, that we had the real insights into how to do it. And so it's been close to 20 years, that's 17 years, 16 years of a lot of hard work, a lot of sweat and tears, so to speak. And when I left my national laboratory job at Jet Propulsion Lab, I figured I'd take a year to work on it and see how far I could get. Yeah. So that sort of says everything, I think. And so there's a sense that I have now that I probably, if I knew then what I know now, I might have taken pause on doing what I did. And yet, as I sit here and I read the news on Lake Mead having gone down from 49% to 39% capacity in 1 year, and maybe the loss of the power generation out of Hoover Dam and all the water that will be withheld from industry and from farms and from people in California and other states, I think we're oddly enough in the right place, California, Silicon Valley, at the right time in terms of there's desperate need for solutions. And I'm hopeful that we can turn the crank in the next year or two to actually get the demos so that we can move quickly with a very manufacturable product that has many uses, both large and small, but will, in one of those applications, that help make a dent in the climate crisis.
Yeah, definitely. I mean, your mission is huge and it needs to be done. And it's definitely that time when we still need to start taking that action, because the time for spreading the message and just protesting, I mean, that's long past. That was like 20 years ago. Now it's the time for us to get active. And so you're really part of it.
Well, and that's exactly the point. There's precious little time to do something. So the people that are there now in all sorts of areas are the people that are going to hopefully solve the problem.
Definitely. And given your history with Giant Leap Technologies, what is one tip that you would give another ecopreneur who's looking to start their green business or grow their green business? What is one tip that you would give them?
Well, I think big pictures that you need to take care of yourself. This is a hard business to get into. There will be many naysayers for whatever it is that you're working on. And you need to have staying power. That staying power probably will not be obvious to you how you're going to obtain that staying power early on. It may be that you have put money away. It may be that you have a spouse that helps you. It may be other sources, but you need to be comfortable with the idea that you're going to be uncomfortable for a while. You will be uncomfortable for a while. It is not a get rich quick scheme. Rather, you need to have the right reasons for doing it. You're trying to do something to better the human condition, and the money will come, hopefully, if you're successful. And if not, at least you've had the courage to try something that's amazing. So you need to really have the right mental attitude, and that you need to think carefully about that mental attitude, what it is you're trying to do. The quality of your thoughts will literally dictate the quality of your life. Be careful with how you're thinking about things.
Yeah, I love that. That's great. And if anybody wants to reach out to you and get in touch with you for partnerships or investing in your company or just interested in supporting you in any way, how can they get in touch with you?
I think the best way is to go to LinkedIn. I have a LinkedIn profile, Leo DiDomenico, DiDomenico, first name Leo, Leo. And it's pretty easy to find me. I'm the only one with solar described in a lot of detail under that name. The name of my companies may or may not fluctuate, so I think that's the best way to go. And I hope to hear from people because this is getting to be a team sport, so to speak, where we need to get as many people helping out as possible, especially after the very early ideas have been crystallized.
Definitely. Awesome. Well, thanks, Leos. Thank you so much for joining us here on the podcast today. I know that my mind was blown like several times just from all the science that we talked about. So thank you so much again for coming on the show. And I definitely hope to have you back on someday. And maybe after you guys have received some funding or got some demos going, and maybe you've got some funding or had some demos go live, and those would be really awesome. Great time to have you back on and see how far you've progressed. So thank you so much for coming on the call today. And I really can't wait to hear from you that you've got some funding or something's come in. So thank you so much again for coming on the podcast.
Thank you, Billy. Thank you so much. And thanks everybody for listening. I appreciate it.
And if you enjoyed hearing all about Leo and Giant Leap Technologies, how they are creating a nanotechnology that is absolutely going to revolutionize our energy transition, I invite you to check out this interview with Rick Navarro. And he talks all about how he has a new invention called Poseidon, where he places it on a body of water and is able to create renewable energy consistently and much cheaper than almost any other energy source out there. So make sure you check out this interview as well for some really awesome new green tech.